Yes.
Okay, very good. So today we'll start discussing some geometry related to Quiver representations. So actually, we've seen already that, if you want, for example, to prove the Gabriel's theorem, it's worth studying representation spaces and the action of the group. However, there are two constructions related to Quivers and their representations, which are of importance for geometry, and these are what so-called Quiver varieties. So they are defined and studied by Nakajima. And another class of varieties are Quiver Grassmannians. So the latter are kind of more down to earth. The former are more complicated. However, both classes of varieties are rather important and show up in many applications and constructions. So let us start with the first class of varieties, the so-called Quiver varieties. And for that, so we consider, as usual, our Quiver Q with a set of arrows, the set of vertices, Q1. And so we need the notion of framed representations. So let me define. So a framed representation of Q is a collection of spaces WK, K being a vertex, and a Q module say V, equipped with the maps WK to, so let me denote these maps by IK, WK to VK for all K from Q0. Okay, so in other words, in order to consider, so a framing is the following. So you consider a representation V, and then to each vertex you attach another space WK and the map from a map from WK to VK. So well, let's use the following notation. So we consider rep U VW to be just the representation space. Maybe I move it. Sorry. Should we do this? So this representation space dimension V plus home space from well, maybe I better write direct sum over K from Q0, home spaces from WK to VK. Okay, so this is the framing, and let me give you an example. So say if Q is just one vertex Quiver with one arrow, Then what do we have? We have space V, and we have a space W. We have a map here. This is our I. And we also have another map, say X, which acts from V to V. So this is a representation on the space VW. Okay. So this is our framing. And so let's do the following observation. So lemma. So the framed representation space rep UVW is isomorphic to the representation space rep U infinity, maybe right infinity downstairs of V infinity of the Quiver Q infinity, which is just well, a new Quiver, Q infinity 0, Q infinity 1. Yeah, so we construct a new Quiver with the set of vertices Q infinity 0 and the set of arrows Q infinity 1, given by such that Q infinity 0 is U0 and one additional vertex, let me denote it by V infinity, and U infinity 1 is U1. So all the arrows which are present in U still well are contained in U infinity. And we additionally add WK arrows from sorry. I use the same notation, but don't have to. So it's just infinity. So just one new vertex. Let me denote by infinity. So WK arrows from infinity to K for all K. And the last thing to say is what is V infinity? So this is a vector such that this is VK for let's see how to say it. So I need the dimension vector, yes, and so maybe you tell me. So what should be the dimension vector to make this isomorphism? So if we want to identify the framed representation space with just simple representation space, so what dimension do we have to take? So any suggestions?
Same
Same.
at vertices of Q node.
Indeed. So V infinity K should be equal to VK for any K in Q0. And what about V infinity infinity?
Sum of W case, I suppose.
And now, if we put like this, why do we have the isomorphism is here? So once again, so what is the rep QVW? So we have the data for rep Q of V. Yes, so all the V-dimensional representations of Q. And clearly, since we are Q is contained in Q infinity, so this is there. And also we need homomorphisms from VK to, from WK to VK. Yes, so is it what we want?
Seems like not. It seems more like we had to not add one vertex, but one vertex for each like WK.
But
And
I mean,
then
this is also possible, but maybe one vertex is enough. So you see, we have WK arrows. Yeah, maybe I draw a picture to make it more clear. For example, say Q is A2. Then we have two spaces, V1, V2. And this is the map here. And then in principle, we have here W1 and W2. But instead, we want to consider a new quiver. Say, assume this is C2, for example. This is C3. So there's this map. And then we add one more fat dot with two arrows here and three arrows here. So just the question is how to encode the left picture via the right picture. So what do we have to put in this fat dot?
Just one-dimensional.
Say it again?
One-dimensional space.
One-dimensional, yeah. Just see. Yeah, because I mean, after all, we have these two arrows here. This means that we have two maps from C to V1. But this is the same as having a map from C2 to V1. And similarly, if we have three maps from C to V2, then it's the same as having one map from C3 to V2. Andrei, does this make sense to you?
yes.
So therefore, here we just put one. Okay. And actually now this lemma is kind of not a lemma, but rather an observation, yeah, because that's just the rephrasement of the definition. Okay.
Well, but is this canonical? I mean, it seems like we fix some basis in WKs if we encode information like that, right?
That's right, yeah, but you see, well, this representation space is the space of homomorphisms, so it's anyway a linear map, and well, this is just a convenient way to write it down. But in principle, right, so we somehow fix the decomposition of the homomorphism from W to V via the direct sum of several homomorphisms. So this is not kind of canonical, but just I don't know, convenient tool for some computations. Okay. Now let's let us do the following. So so as let me denote by R the framed representation space RVW, and so what I want to maybe sorry, I denoted by rep. Yes. So then let me consider T star of R. So this T star of R is just R plus R star, because so this R is nothing as in just an affine space. So therefore it's cotangent bundle, or well, it's a fancy word here, but it just means that R plus R star. So what is that? Let's write it explicitly. So our R, so just again an observation. So T star R is the collection of the following data. So we have the maps XA and YA. Yeah, maybe I should write it separately. So XA is a map from VS of A to VT of A, and YA in an opposite direction, VT of A, VS of A. So this is for all A from Q1. And also we have maps IK from WK to VK, and JK, VK to WK for any K from Q0. So this is T star R is the collection of the following data. So each point is determined by four collections of maps. So the first two are parameterized by arrows in our Quiver, and the second two are parameterized by vertices of our Quiver. Okay.
Oh, sorry, why don't we take V star for YA?
So let's see. So what is the what is the, say, I don't know, we have a map from V1 to V2. So this is our map XA. So this is the homomorphisms from V1 to V2. Now the dual guy is hom V1 V2 star, right? So how this can be considered? So this homomorphism space is the tensor product V1 star tensor V2, right? So now the dual is V1 tensor V2 star, which can be identified with hom V2 V1. Okay, so
Okay,
this, sorry?
thank you. Now I understand.
Okay, good. So therefore, so in principle, one might want to work with the dual spaces, but instead it's convenient to consider, to forget about duals, but to kind of reverse the maps and to consider the collections of maps in the opposite direction. Okay, so that's it. Maybe some examples. So first, several examples. So one, maybe very trivial one, is Q being just one vertex, nothing else. Then this P star R is just home VW plus home WV. This is the map I from here and the map J from here. So it's just the collection of pairs of maps between the two vector spaces. So another example, a bit less trivial, is as we had before. So this is a loop quiver. And then for this loop quiver, this T star R consists of the points parameterized by 4 tuples of maps. So these are X, Y, I, J. Let me draw the picture. So we have a map, we have a space V, and we have a space W. And here we have mapping X. And since we have only one space, the map Y is also acting from V to V. And now there are two maps between V and W. So there is a map I from W to V, and there is a map J in the opposite direction. So we can identify, so this is the space, is just the end V twice plus home VW plus home W. Okay. This is our second example. Maybe the last example here is the A2 quiver. Like this. Then the picture is as follows. So we have V1, V2, and W1, W2. And we have a map X here and the map Y in opposite direction. And also we have two maps, 4 maps actually. So we have map I1 and J1. And then we have a map I2 and J2. Okay. So the space is and V1, V2 plus and, oops, sorry, home V1, V2 plus home V2, V1 plus home V1, W1, home W1, V1 plus home V2, W2, home W2. Okay. So this is our space we are going to work with. And now one of the main definitions here is the so-called moment map. So maybe before that, sorry. So let me put forward the following remark. So let us consider G to be GV to be the group which is the product of GL VI or VK K0. So this is our standard group which acts on the representation space, and the remark is that the group GV acts on R on this rep Q VW. So I mean, we've seen that the group G does act on the representation space itself. I mean, on the rep Q of V, and then we add homomorphisms from V from W to V, and of course the action is still there. So I mean, you can act via the action of V, so GV does act here. Okay, so now let's put forward the following definition. So we want to construct the map mu from T star R to, maybe I should denote just by okay, doesn't matter. T star R to GLV, which is the direct sum over K GL VK. Okay, so this is the map we want to consider, and actually we have to define mu of the collection X A V Y A I K J. Can you suggest a definition? So can you invent some map which lands in GLV? Just try to imagine what you can do with these maps in order to get an element from GLV. So any suggestions?
Well, to compose them.
That's right. Let's try to compose. So actually we have to arrive at a collection of maps from VK to VK. So we have to give a collection of maps labeled by a vertex. Labeled by, well, for each vertex we have to define a map. So how can we compose? So first of all, we can take the products XA, YA. So what should be a condition on A in order to guarantee that this product is in GL of VK? So recall that axis is a map from S of A to VT of A, and Y vice versa. So for what A, this product sits in GL of VK.
Well, if K equals T of A.
Yes. So we take the sum over all A such that T of A is K. And we subtract the guys which are given in an opposite direction. And here S of A should be K. And what else can we do? So here we composed X's and Y's. And now what else? What else can we do?
Compose I's and J's.
Right, right. Just we can write I, K, J. So JK is a map from V to W, and then we are back by the action of I. Okay. So this is the definition. Let's see some examples. So if Q is just one vertex quiver, so what is mu? Can you tell me?
IJ.
Absolutely. So mu of ij. So we have no x's, no y's, just ij. So let's consider the next example. So if Q is one vertex and one loop, so what is mu? So here we have one vertex, one loop. So the mu should be a bit more complicated.
Well, it's ij plus the commutator of x and y.
Indeed. So first of all, mu acts on collections x, y, I, j. So x and y are mappings from our space to itself. And I and j are maps between v and w. So we have xy minus yx plus ij. Okay, and then finally, let's consider our third favorite example. So Q is A2 quiver. And what is mu here? Alex, do you know?
I'm a bit confused. Don't we have to fix some dimension vector?
Say it again?
Don't we have to fix the dimension vector?
Yes, for sure. So actually, we assume that we have spaces V1 and V2, right? And we also have spaces W1 and W2. And this is our data. So we fix the dimensions of V1 and V2 and dimensions of W1, W2. These are vectors VW from our settings. And we also have a map X from V to 1 to W and the map Y. And here we have maps in two directions, I's and J's. So the question is, what is mu applied to X, Y, I1, I2, J1, J2? Just by definition. So any suggestions?
Well, the first component should be minus yx plus I1, J1, and the second XY plus I2, J2.
Alex, Andrei, do you agree?
Yeah.
Yes.
Okay. So these are our example, and now the idea is that we are interested in mu inverse of 0 modulo the action of GLV. Yeah, so in other words, we want to see the 0 level of the moment map, so the pre-image of 0. And also we are interested in orbits of V rather than of the whole pre-image itself. So the reason why this makes sense will be clear from the examples we are going to have below. But so far, this is a kind of somewhat general construction for moment maps. And so as for the action of the GLV, this means that we are interested not in kind of basis, but in the structure of the space itself. Okay, but the problem is that the action of GLV on the mu inverse of 0 is not always good enough. So for that, we have to make the space on which the group acts a bit smaller. So let us introduce the following definition. So the GLV action on mu inverse of 0 is not always good enough. So we have to introduce the following definition. So we have to pass to the semi-stable part. Let's define that. So let us fix vector psi in z greater or equal to 0 to q naught. So after all, psi is a collection psi k from 0. Sorry. Does not have to be non-negative. Just arbitrary integer. Actually, it's not necessarily an integer, even that. So maybe I even forget about this condition. So just arbitrary real numbers, one real number for each vertex. Okay, so those real numbers can be positive, negative, 0, whatever. So now the definition is as follows. So a point xa, ya, ik, jk in R, in T star of R is called psi semi-stable if the following conditions hold. So the first condition is as follows. So if sk K from Q0 is a collection of subspaces of K such that first of all, S, this collection is invariant with respect to all maps xi, y, xa, ya, and second, sk sits in the kernel of I. So let me check if I'm sorry, of course, in the kernel of jk. So this is the first condition. Then sk is 0 for all k. So what does the condition say? It says that if you are given a collection of subspaces of vk, so one subspace for each vertex, such that those guys are in the kernel of jk. So this means that the restriction of jk to sk is 0, and sk is invariant with respect to xa and ya, then you have no such a collection except for just trivial one. Okay. And oh, sorry, this is already a special case because psi is not here. But what I wanted to say then psi of the dimension of S is less than or equal to 0. So psi of dimension S is the sum psi k dimension. So we'll see why I wrote that S is 0 in a minute, but so far the general definition is given here. And then the second condition is that if tk, again labeled by the same set, is a collection of subspaces of vk, such that sk, sorry, tk is invariant with respect to xa, ya, and tk contains the image of ik for all k, then psi of dimension S is greater than or equal to psi of dimension B. And of course, it's not S here, but right. Should it be greater than or equal or less than or equal? Let's see. I think less than or equal, but we'll see in a minute. Okay. So is it clear what's written here? Okay, so let us consider an example. So in order to see what's going on. So assume psi k is strictly positive for all k. Okay. So so what can you say about the second condition?
it always holds.
Alex, Andrei, do you agree?
Yeah.
So then,
Yes, since it's collection of subspaces. Okay.
yes, the condition 2 holds automatically. And what does condition 1 say?
S are zeros.
Right, right. So so if psi sits in R positive to Q0, then point XA, YA, IJ is psi semi-stable if for any collection SK such that SK sits in the kernel of JK, and SK is XY invariant. One has SK is just 0. So this is our condition, and so we'll be working with this or similar guy. So assume now that we have an opposite condition, xi k is strictly negative for any k is q0. So then what does the first condition say? So what's the meaning of condition 1 on the subspace S?
It always work,
Right.
right? Also,
Absolutely, yeah. So then condition 1 is just empty, right? Does not say anything. And what does condition 2 say?
That it's irreducible.
What is irreducible?
I mean, it's simple. There can be no proper subspace.
So let's see. So T is invariant with respect to X, A, and Y. In this sense, T is indeed a sub-representation, but with some extra condition, right? So it has to contain the image of IKs. So we are not saying about arbitrary sub-representation, but only about those sub-representations which contain the images of IK, right? And what is our actual condition? So what is, how can we simplify it? Or write in a more concrete terms?
These images generate our representation.
Indeed. So the condition that psi of dimension t less or equal to psi of dimension v, when does it hold? So if psi is strictly negative.
When t is equal to v.
Right. So, and so this means that condition 2 says that if t in v is a subrepresentation such that T contains the image of I, right? Then T is just. So it's not irreducible, but it says that if subrepresentation contains all the images of all I's, then it's just the whole thing. Okay. So let's maybe first, what do we do? What do we do? Yeah, maybe let's finish the definition and then we look at some examples. So let me state the following theorem. I'm not going to prove this. So yeah, maybe I should say here that we are going to work only with psi from R positive, you know, or psi in R negative. So in this case, we have the following theorem that the group GLD acts on mu inverse 0, same, yeah, sorry. So it means I use the following definition or notation. Mu inverse 0 semi-stable is the set of semi-stable points in mu inverse. Do I need something else? Maybe not. Maybe not. So the group acts on this freely, and the orbits are closed in inverse 0 as. So, well, you can just think of that there's no stabilizers exist at all. So the action is free. And also all the orbits are good. So it means that they are closed. And then you can just consider the space of orbits. Yeah, so now the definition, the main one. So the Nakajima Quiver variety MVW is by definition mu inverse 0 semi-stable modulo the group G. Okay. So this is the definition, and of course we have to work out some examples to see whether it makes sense at all and what are we talking about. So let us look at the simplest example, Q being just one vertex quiver, just A1. And so we're given V and W, just two numbers. So what is mu V W? So for that, of course, we have to say what are the stability conditions. So let's assume that psi is positive. So psi is just one number, and assume this number is positive. So so can you tell me what is so first of all, so our T star R consists of pairs I, J. And what is T star R semi-stable? So what does our condition say? So what are the semi-stable points of the cotangent bundle to the framed representation space? Assuming that the stability condition is positive. And let me once again repeat that the stability condition, in this case, just a single real number.
J should not have kernel.
Why J? So let's see. Let's see. So what does in this example? Yes, we have. Yes, J. Yes. Mm-hmm. Absolutely. So consists of pairs I, J, such that J is an embedding. So Alex, do you agree? Shall we elaborate on this?
I think it's reasonable.
Say it again, please.
I think it's okay. Yeah.
So simply because this is our first example. Oops. Here it is. Yes, and it says that S is 0 if it is contained in the kernel and XY invariant. But there are no X's, no Y's. So this no condition on the XY invariance. And then the claim is that if we have something in the kernel, then this something has to be equal to 0. Therefore, there's no option other than just having no kernel at all. Oh, good. So J is an embedding. And so now, what is mu inverse 0 semi-stable? So what pairs we're interested in? Ij such that what?
I is subjective.
Say again?
I is subjective.
Why? Psi is still positive. Yeah, so we have the same.
Oh, it's, yeah, sorry, yeah.
Same stability condition. So what are the semi-stable, how to describe semi-stable points such that mu is of them is 0?
I is 0.
Why?
So the composition should be 0.
The composition should be 0, but this does not imply that I is 0, right? Because J is an embedding.
Yeah, sure.
So J, the kernel of J is 0, and composition Ij is 0. Okay, and now we are interested in what is the mu inverse 0 semi-stable modular GLV. So actually, I claim that this is something reasonably concrete, but for that, let us try to somehow understand. So what is that? So let me draw the picture. So we have V, we have a W, and we have J, which is an embedding from V to W, and also we have I, such that the composition of I and J is 0. This means that I evaluated on the image of J is 0, right? So very good. So this means that after all, I is a map from W modulo the image of J to V. Okay. And so we consider, so let us consider the following data. So if we consider subspaces of dimension V inside the space W, modular the group GLV. So what is that? So rather not the subspaces, but rather, maybe I should write it more concretely. So the injective maps from CV to CW modulo GLV. So please raise your hand if you know what is this object. So we consider a V-dimensional vector space and a W-dimensional vector space, and we consider the embeddings of V-dimensional vector space into W-dimensional vector space modulo GLV. So what is that? I claim that this is something very, very concrete. Okay. So Andrei, can you tell us what that?
It's like just subspaces of dimension equal to dimension of V in CW.
Yeah, so how this variety is called?
Grassmannian.
Right.
Grassmannian.
Yes. This is Grassmannian of V-dimensional subspaces in a W-dimensional subspace. Yes, so, well, I mean, how to say, this is actually, after all, this is obvious because, well, so what is a Grassmannian? So these are, Grassmannian consists of points, each point being a subspace in a W-dimensional vector space, right? So now how you can look at the subspace? So this is a, well, this is the image of some kind of formal or given V-dimensional space, yeah? But you don't care about the bases or ordering of the images of bases or whatever. So you only care about the space itself. So you consider injective maps, So does not have, well, necessarily there should be no kernel, but after that you quotient by the action of GLV, since you don't care about the actual basis of your space. So, well, sometimes it's written like Grassmannian VW is isomorphic to Hom 0, where 0 refers to injective maps from CV to CW modulo GLV. So this is the first thing. And the second thing is that we see here that Nakajima Quiver variety is 0 unless V is less or equal than W. So it's not quite clear from the definition, but in this case, so in order to guarantee that this variety is non-empty, we should impose the condition that V is less or equal than W. Okay. Okay, so we are almost there, but so what is the conclusion so far? Conclusion so far. So there is a map from MVW to Grassmannian VW, just sending pair ij to image of j. Right? And what's the fiber of this map? So we decided that after we quotient the homomorphism space, maybe I should write that this 0 is injective. So what's the fiber? And actually, this is the map onto. Yes, so since any subspace can be obtained as an image of some linear map.
The fiber should just be GL.
Serene?
GL.
What GL? So, I mean,
Of V, right?
No, you remember that this guy is equal to mu inverse 0 semi-stable modulo GLV. So this means that kind of each point here is a class of some pair ij. So GLV is not contained in MVW.
Yeah.
Rather, we consider the orbits of GLV with respect to the action on the semi-stable part of the 0 fiber of the moment map, right? And our map somehow considers the, I should write here the class of ij, and this is mapped to the image of j. Okay? So the question is, what's the pre-image of a given subspace? So suppose we denote this map by phi. So what is phi of some phi inverse of some subspace V? So how to identify it? Any suggestions? So let us maybe repeat what we have so far. So we have a pair ij, and then given such a pair, actually the orbit, the GLV orbit of such a pair, we map this orbit to the image of J. So of course, the action of GLV does not change the image of J, since I'll tax only on V itself, and the image belongs to W. So now, well, of course, pair ij is not determined by the image of J. So we somehow, the question is as follows. So what are possible pairs ij from mu inverse of 0 semi-stable with the prescribed image of J? So if the image of J is fixed, we are asking for what are possible pairs ij with the same image of J.
Well, I should be a map from the quotient by this image to V.
Right. That's right. And so have you seen such an object? So what is it responsible for? So actually I claim that hom W mod, so let me formulate it. So let V be a subspace in W. Then home space from W mod V is isomorphic to the cotangent space to Grassmannian VW at the point V. So our V here plays a role of, maybe I should put N here, not to mix it with the V we had before. So N be a subspace in V, so the dimension of N is small v. Okay, and then we consider home space from V mod N to N, and the claim is that home space is isomorphic to the space, the cotangent space to the Grassmannian at the point N. Or in other words, this can be rephrased as the home space in the opposite direction from N to W mod N is isomorphic to the tangent space to Grassmannian VW. So is it clear why? So maybe let us draw the following picture. So, well, we have our n. So assume that, let us prove them, then it's important for the understanding. So assume that, say, E1 up to EV, the basis of n, and EV plus 1, EW, well, this is the complement to E1 EV to a basis on down. Okay, so we have some basis of V of n, so our fixed subspace, and we somehow completed to a basis of W. Then what is a Grassmannian after all? So let me draw a matrix. And this is W by W matrix. A bit more accurately. So have a matrix. And here we have basis vectors E1 up to EV, EV plus 1 up to EW, and E1 up to EV, E plus 1, EW. And then, let me just write in the columns the basis vectors for n. Yes, so these are, maybe I just even erase the upstairs line. So let me just write, maybe, sorry, let me do even simpler. So I can see the matrix, which is V times W size. So here we have V, columns, and W rows. And so in each column, we have some vector, which say such that the span of these V vectors is some subspace. And then I claim that in the vicinity of our space n, any vector is given by some matrix, which is star here. So star is an element in, so this is home and to E1 up to EV from n to W mod n. So the claim is that star, so all points in the vicinity of n are determined by the matrix star, and determined by the very exact way. So you see if I consider the matrix, which we have on the screen now, then the columns of this matrix, they span an V-dimensional subspace of W, okay? And if the star matrix is 0, then the subspace is exactly our n. Otherwise, this is some subspace which is very close to n, or maybe not very, but close. At least why I want to say that these star matrices, they determine, well, kind of tangent space to the Grassmannian, very explicitly. Yeah, so this is the kind of identification of a point nearby or close in the vicinity of our n. And you see that this is exactly the homomorphism space from n to Wn. Okay. So any questions about this claim and about this computation? So maybe let me summarize this. with the following proposition.
Sorry, is this cotangent space or tangent space?
Yes, so let's see. The claim says that if n is so that the cotangent space is a homomorphism from W mod n to n. Okay, so the dual to this space is the homomorphism space in the opposite direction. So we want the
Okay.
tangent space to be homomorphisms from n to the quotient of the large space modulo our subspace. Okay, and this indeed the tangent space. So since we identify the points in the neighborhood of our n. So the proposition says that if U is A1 and the stability condition psi is positive, then the Nakajima-Quiver variety is empty if V is greater than or equal to greater than W, if V is less than or equal to W, then the Nakajima-Quiver variety is isomorphic to the cotangent bundle to the Grassmannian V-dimensional subspaces in a W-dimensional vector space. Okay, and this is your homework. So describe, well, I will upload it, but anyway, so the homework is to describe the Nakajima-Quiver variety for Q being still A1 and psi being a negative number. Okay. Okay, so maybe it's time to stop now. So any questions, comments, remarks? So if not, I stop sharing. And so next time we'll spend a bit more time on discussing maybe some more examples, and then we'll go to the discussion of Quiver Grassmannians. And so that's it for today. So if you have no questions.